Okay, let's try something. When you think of the ground, right under your feet, what's the first word that pops into your head? For most of us, it's probably just dirt, right? But what if I told you that dirt is one of the most misleading words out there? Seriously. We're about to take a tour of this amazing, unseen chemical factory that's right beneath us, and it all kicks off with one simple but really important question.
So what is the difference between dirt and soil? I mean, you might think they're basically the same thing, but chemically, biologically, they are worlds apart. It's not even close. One is totally lifeless, and the other, well, the other is the very foundation of life as we know it.
And here it is, laid out plain and simple. Dirt is just inert, crushed-up rock. It's lifeless. But soil is a living system. The source material for this actually calls it a biogeochemical engine, which is such a cool way to put it. It's a dynamic, breathing thing that's constantly exchanging matter and energy with the air, with water, and with life itself.
Okay, so if soil isn't just crushed rock, what is it? Let's dive into its secret formula, because this is where the chemical story gets really, really interesting.
Here's the most crucial point to get. Soil has a completely different chemical signature than the rock it came from. This isn't just a physical change. It's a deep, profound chemical transformation, and it's driven by one key ingredient, life.
So, check out these numbers. It's pretty wild. You see elements like calcium and sodium, they get washed out. They're depleted over time. But then, look what happens to carbon and nitrogen. Carbon jumps up by a factor of 8, and nitrogen, wow, it skyrockets by over 30 times. So where does all this extra stuff come from? It's all from organic matter. We're talking about all the plants, the microbes, everything that lives and dies in the soil.
And just look at that massive jump in carbon. That isn't just a number on a chart, that's the chemical fingerprint of a living system. By grabbing and storing these elements, soil literally breathes life into rock, creating the fertile ground that keeps us all alive. This right here is the fuel for the entire engine.
But here's the thing. This natural recipe, the one that's been perfected over millions of years, it's now being rewritten. Our human fingerprint is starting to alter this incredibly delicate chemical balance on a planetary scale.
So to measure our impact, scientists have this metric called the anthropogenic mobilization factor, or AMF for short. It's actually a pretty simple ratio. How fast are we digging an element up compared to how fast nature releases it? You see a value way above 1, and you know we've seriously messed with that element's natural cycle.
Okay, get ready for this. For copper, we're mobilizing it 632 times faster than all the world's volcanoes and weathering processes put together. 632.
For mercury, which we all know is a potent toxin, that number is 342. We've just completely overwhelmed its natural cycle.
And for chromium, it's 273. Look, these aren't small changes. We are fundamentally changing the chemistry of the Earth's surface, and a whole lot of this material is ending up right back in our soils.
So, we're moving massive amounts of these metals all around the planet. But why does that matter? What's the big deal? Well, the answer is in the very specific chemistry that makes some of these elements so incredibly toxic.
And that's a fantastic question, isn't it? I mean, our bodies need metals like calcium and potassium to work. We can't live without them. So what makes something like lead or mercury so different, so dangerous? It all comes down to some really basic chemistry.
The source material gives us a pretty simple, two-step test to figure out if something's likely to be toxic. First, does it dissolve in water? And second, what kind of chemical bonds does it like to form? Does it form weak ones or really, really strong ones? Chemists call this its Class A or Class B property.
Okay, let's try it out. Think about calcium, right? It's essential for our bones. It forms weak bonds, which means it can do its job in a cell and then easily let go and move on. Now look at lead. Lead forms these incredibly strong, tenacious bonds. So when lead gets into your body, it can literally knock an essential metal like calcium out of its spot, and then it refuses to leave. It just gets stuck, permanently wrecking critical biological processes. And that right there is the chemical root of its toxicity. So to sum it all up, toxicity is tied to metals that either don't dissolve in the first place, meaning life never really evolved to use them, or they're the ones that form these super strong covalent bonds that let them hijack our cellular machinery.
So, we've seen what soil is, we've seen how we're changing it. For this last part, let's just zoom all the way out and put this moment into the context of soil's really deep geological history. What's so important to remember is that soil isn't static. It never has been. Over millions of years, it naturally evolves through these predictable stages. Young soils are really rich in minerals, but as they get weathered by water and life, they transform, and eventually they become those deep red, iron-rich soils you see in the tropics. The point is, soil has always been in a state of flux.
And this brings us right to our final question. The ground under our feet has always been changing, always evolving over geologic time. But our fingerprint, this massive mobilization of toxic metals that form these stubborn, tenacious bonds, is happening in the blink of a geological eye. So the real question we have to ask is, what is our legacy going to be in this ever-changing chemical story of soil?